Well, here we are. We made it to the end of chapter 12. So on this section, we're going to be discussing a little bit more on enthalpy. So let's finish the enthalpy objective before we move into phase diagrams. So we did a lot of problems on part D in which we were given the enthalpy of vaporization, the enthalpy of fusion, and all that. And where are those numbers coming from? That basically tells us how much energy matter contains or releases or absorbs. So where are we getting these numbers from? And these numbers are coming from being able to measure pressure and temperature. And very smart people have been able to put those together into formulas. And one of these formulas is the Clausius-Clapeyron equation. The Clausius-Clapeyron equations help us find the enthalpy of vaporization by measuring something that is very easy to measure on the lab, by measuring pressure and temperature. If you have a gauge, you can easily measure the pressure that the gas is putting on that gauge. And how do we measure temperature? Super easy with a thermometer, right? By to make measurements, you can find something that it's kind of an abstract concept sometimes, the energy of matter itself. So this is the beauty of going to the lab, that you can come up with things that are really hard to measure by measuring really easy stuff. So this formula can be presented in two formulas, in two different ways of seeing it. If you notice, the first one follows the format of a straight line, which basically means you can have a line with the y-axis and the x-axis, where the y-axis is going to be the natural logarithm of the vapor pressure, and the x-axis is going to be the reciprocal of the temperature. So if you measure those numbers, you're going to come up with a line like this because it follows the format of a straight line with a negative slope, and the slope of this, which is the change in y over the change in x, on this particular case, is going to be the enthalpy of vaporization over the R constant. And the R constant you learn in chemistry 1 or chemistry 1411 is 8.31 joules moles Kelvin, or 0.08206 liters atmospheres moles Kelvin. However, given that we're dealing with energy, this is the one that we need to use, the one that contains energy. So by collecting pressure and doing the natural logarithm of the pressure, of the vapor pressure, and by reading the temperature and doing the reciprocal of the temperature, you can do a graph, and directly from the graph, you can find the slope, and the slope is going to give you the enthalpy of vaporization divided by the R constant. So basically, if you multiply by the R constant, you get the enthalpy of vaporization. So that's a very easy way going to the lab to find those values. What about the second way? The second way we can express the Clausius-Clapeyron formula. The second way of expressing it is by using 2 points, by using pressure 1 and temperature 1, and pressure 2 and temperature 2. The beauty of this way of writing the Clausius-Clapeyron form is that if you know 2 pressures and 2 temperatures, you can find the delta H of vaporization. But if you know the delta H of vaporization by using the first formula, then if you know pressure 1 and pressure 2 and T1, then you can find T2. So it's a different way to start predicting. So if I know the delta H of vaporization of water, and I'm measuring the pressure on this condition and the pressure on this condition, and I know the temperature for pressure 1, now I can predict the temperature that is going to require to make it all the way to pressure 2. So you can control experiments and you can say, I don't want this experiment, for example, to exceed so many degrees. So you can calculate how much pressure that's going to be, and that can allow you to decide what type of glass to use. Do I need to use a stronger glass for this experiment? What temperature to use? Can I afford to use that much temperatures, and so on? So these are two very powerful ways of using the Clausius-Clapeyron equation, which allow us to relate the natural logarithm of the vapor pressure versus the reciprocal of the temperature, and that temperature has to be in degrees Kelvin. So basically, if you know the vapor pressure and you know the temperature, you can find delta H of vaporization. Very powerful formulas. So let's see how we're going to use them. So let's do this problem. So ethanol had a heat of vaporization. So this is given of 338.56 kilojoules per mole. And a normal boiling point, normal. What does normal means? Well, normal is what is normal for us right now. For example, if I go out right now and start walking on the street, the pressure that I'm gonna feel is 1 atmosphere of pressure. That's what normal. 1 atmosphere of pressure is normal because that's what the planet has. So every time you hear normal boiling point, that means the boiling point at 1 atmosphere of pressure, or the boiling point at 760 milliliters of mercury, or the boiling point at 760 torrs. Remember that from Chem 1. So that's what normal means. So that means that the pressure is 1 atmosphere because it's normal. So ethanol have a heat of vaporization of that much and a normal boiling point of 78.4. So it's telling us that P1 is 1 atmosphere of pressure, T1 equals 78.4 degrees Celsius. So normal is a super important key there because it's telling you it's 1 atmosphere. What is the vapor pressure of ethanol at 15 degrees Celsius? So what would be the next pressure when the temperature equals 15 degrees Celsius? So obviously, this is data that is offering us 2 data points, which means we are going to be using this formula. So what do we have? We're going to have natural logarithm of P2. That's what we are looking for. That's our unknown over P1, which is 1 atmosphere, equals negative 38.56 kilojoules per mole over 8.31 joules moles Kelvin. Notice that this is joules and this is kilojoules, so that will be a problem. So what I'm gonna do is I'm gonna make it the same. So I'm gonna make this 0.0031 kilojoules. You know from Chem 1 that you can go from joules to kilojoules by dividing by 1,000. So that's what I did. So that will cause this, and then we're gonna multiply that by 1 over T2 is 15 degrees Celsius, but it has to be on Kelvin, plus 273.15. That will make it Kelvin minus 1 over 78.4 plus 273.15. So when we do, and I tend not to solve these problems, I just want to show you how they are done. The rest is just math. This is a chemistry class. So once I plug my numbers on the formula and I take care of the unit, like kilojoule has to match with kilojoules, the kilojoules would cancel with the kilojoules, the moles would cancel with the moles, and the only thing we're going to have remaining here is going to be the Kelvin. But once we multiply by this factor, we're going to get our units 1 over Kelvin. Let me fix this a little bit. So our units at the bottoms are going to be 1 over Kelvin. So the Kelvin would cancel the Kelvin. So the only remaining thing is going to be our unknown. So from there on, that's just math. So make sure you can solve for P2. If you have problems solving the math part of this, I can meet individually with you, either through Microsoft Teams or in person. But we're not going to put time on doing the actual math. I just showed you how to use the formula. I know you know this math because you are here, so you already took all the prerequisites. So if you have any question on this, make sure you let me know, please. So let's do another one. Methylamine has a vapor pressure of 344 torr at minus 25 degrees Celsius and a normal boiling point of minus 6.0. So once more, this is going to be, we're going to call this one P1. This one is going to be T1. This is going to be T2. And the normal boiling point is normal. So 1 atmosphere will equals P2. Find the delta H of vaporization. There's 2 ways to do this. You can just take one set. You can plug P1 in there. You can plug T1 in there. You don't know what this is, so you cannot just solve it like that. But you can, since we know this follows a line, right? You can do LMP over 1T. You can change all the temperatures to Kelvin, and then you're gonna have, you can find ln of P1, you can find 1 over T1, and put that on the graph. Then you can find ln P2, and you can find 1 over T2. Make sure that's Kelvin. You can put that on the graph, and then do the line, find the slope, and you found delta H of vaporization. So you can do it like that, or you can use this formula by plugging the numbers there. If you use that formula, be careful. Why do you have to be careful? Because you gotta make sure that the units match, right? Remember, your R, the R that you're using is 8.31 joules moles Kelvin. So T1, T2 and T1 have to be Kelvin. P2 and P1 they do not have to be atmospheres, but since you know that normal means 1 atmosphere, you also know that it equals 760 torrs. So whatever pressure you decide to use, atmospheres or torrs, both of them will have to be the same. So make sure that P2 and P1 have the same units. The unit that you're using doesn't matter because it's going to cancel, but they have to be the same unit. You either use atmosphere for both or you use torque for both. And then it just becomes a math problem. So here's your daily work. Give you about 3 seconds so you can pause it without rushing. Pressing on. So with this, we have talked everything we can talk so far about the changes of states, deciding if they are endothermic or exothermic. We know how to draw heating or cooling curve. We know how to interpret enthalpy changes, and we now know how to get those values by going to the lab and measuring pressure and temperature and using the Clausius-Clapeyron formula. And we see how they relate to phase changes by the formulas that we studied for Q, amount of matter times the delta H, or matter, the amount times the change in temperature times the specific heat. So once more, if there anything that you need to go deeper, that's what the book is for. Go back and review, read. Now you can read with a purpose, knowing what you really want to understand. You can watch the tutorial videos the same way. And Office and Science Learning Center are always available. So new objectives, phase diagrams. So what is a phase diagram? A phase diagram is nothing more than relating data of pressure and temperature to see how that changes the state of matter. So remember, on a solid, except for water, on a solid, the particles are very close together. On a gas, the particles are very far apart. So if I increase the pressure on those particles, I'm forcing them to come closer together. As they come closer together, the intermolecular forces will take hold, and then you can take a gas and make it into a liquid. You can take a liquid and make it into a solid just by putting pressure. So at 1 atmosphere of pressure, water will boil at 100 degrees Celsius. But if the atmosphere was like 100 atmospheres, when I put in a lot of pressure on those molecules, they're going to be closer together, the intermolecular forces are going to be stronger, and it's going to take a lot of energy, a lot more than 100 degrees Celsius, to get them to move. So we can see, and that's why we use a normal boiling point to indicate that that's only true at 1 atmosphere. So by playing with the pressure, we can play with the states. Super important for engineering and medical procedures, because if the atmospheric pressure where I'm doing this, especially if you're going into traveling to space or something like that, where the conditions are going to be different, that can affect how matter is going to behave, and that can throw off everything out of sync. So let's look at this this diagram. And it's asking us to identify the states present at points A through G. So point A, what would that state be? Well, at point A, the pressure is very low, and it begins to increase. So all this here, the pressure is increasing as the temperature is also increasing. So as the pressure increases, the molecules are coming closer together, and there's a point here where the temperature doesn't change. So as the temperature goes up, the molecules begin to move faster. You start losing intermolecular forces proper alignment, and something is going to change. So this line here is where the phase is changing. So as the temperature increases, we know that you can take a solid and convert it into a liquid. You know you can take a liquid and make it into a solid. So I'm going to say that at the lower temperature, once more, lower temperature and lower pressure, that's where the molecules are be the closest together. So this is going to be where my solid is going to be. As the temperature goes up, the solid is going to transition into the liquid. And as the temperature continues going up, the temperature is going to transition into a gas. So solid, liquid, and gas. And you also have a transition here where the solid is going to gas. So on these phase diagrams, we can see this as melting. We can see this as boiling, crossing that line. Or we can say that this is the equilibrium line between the liquid and the gas. This is the equilibrium line between the solid and the liquid. And this is the equilibrium line between the solid and the gas. So this is what we're going to call sublimation. So let's go back and identify exactly what the problem wants. I kind of took like a short tangent in there. So point A, that's going to be solid. Point B, that's going to be liquid. Point C, that's going to be gas. Point G, you're going to have the solid, the liquid, and the gas all in perfect equilibrium. So you're going to have all three phases on a perfect equilibrium. That's what we call this the triple point. So the triple point is where all three phases are in perfect equilibrium. On E, that's where we have solid becoming liquid and liquid becoming solid. So we have solid and liquid present in equilibrium and that one. And then on F, that's where we have the liquid in perfect equilibrium with the gas. The arrows means that it goes from liquid to gas and then it goes back to gas to liquids, back and forward in perfect equilibrium. And then on D, what we have is weird. On D, the temperature is so high that it doesn't matter how much pressure you put, you're not going to take the gas and make it into a liquid. So we call that the supercritical phase. Molecules are moving so fast because of the higher temperature. It doesn't matter how much pressure you put to bring them together to make it into a liquid. It remains on a kind of weird gas liquid section there, but it's not an equilibrium. So let me know if you have any questions on this. So let's assume that this was 1 atmosphere. If this was 1 atmosphere, then this point here will be what we call the normal freezing point or the normal melting point because it happens at 1 atmosphere And this one over here will be the normal boiling point. Remember, normal means 1 atmosphere. So another problem, consider the phase diagram for iodine and answer each question. What is the normal boiling point for iodine? Well, 1 atmosphere is normal. This here is solid to liquid, so that's not boiling point, but liquid to gas, that's boiling point. So the normal boiling point is going to be 184.4 degrees Celsius. What is the melting point for iodine at 1 atmosphere? That's going to be 113.6. So at 1 atmosphere, which is the normal, this is solid to liquid, so that's melting, and that's going to be 113.6. What state is present at room temperature and normal atmospheric pressure? So normal atmospheric pressure, once more, is 1 atmosphere. So it's asking that pressure and room temperature. Room temperature is around 25 degrees Celsius. So this would be 100. I would say this is close to 50, approximate. So this would be around 25. So a very rough approximation at 1 atmosphere, at room temperature and normal atmospheric pressure, so that would be around this point, right? 25 degrees and 1 atmosphere, that's going to be a solid. What state is present at 186 and 1 atmosphere? 186 will be kind of right in there. That will be 186. And 1 atmosphere will be right there. So that's going to be my gas section. So that will be your gas. Remember, solid, liquid, and gas. And that's basically what we do with this, understanding how we use the phase diagram. So that's your daily work. And with that, you have been introduced to the phase diagrams. You know where the critical pressure is. You know where the critical temperature is. Let's review that. So at the end of the equilibrium line between the liquid and the gas, that's your critical point. So that means that this is your critical pressure and this is your critical temperature. So that's why it's so good to review the learning objectives always at the end to make sure I didn't forget anything. We understand what vapor pressure is. We know what normal boiling point is. We know what normal melting point is. We just review the critical point, and you know where the triple point is, which is the point where all 3 phases are in equilibrium. That's your triple point. And with that said, here are all the objectives that we went for on this chapter. Quick review. Identify intermolecular attractive interactions. Remember, all matter have dispersion because they contain electrons. You're going to have dipole-dipole interactions. For that to happen, the molecule has to be polar. So make sure you review your material from 1411 on how to determine if a molecule is polar or not. And then hydrogen bonding only happens when you have hydrogen attached to fluorine, or a portion of the molecule contains OH, or a portion of the molecule contains NH. And then you know that the dispersion is the weakest depending on how big the molecule is. The bigger the molecule is, it could be that it's stronger than dipole-dipole. And then it's followed by hydrogen bonding, and then the ionic. and we saw that you can have a very non-polar molecule doing going its day, behaving well, and something come close to it, disturb the electron cloud by momentarily pulling the electrons, and it can create polarization and create a temporary partially positive, partially negative. That's how dispersion forces come to be. And then by understanding the intermolecular forces, we know how that affects the boiling point. The stronger the intermolecular forces, the higher is the boiling point. The stronger the intermolecular forces, the lower the vapor pressure, and you should be able to explain why. The stronger the intermolecular forces, or the bigger the molecule, the stronger the viscosity, the stronger intermolecular forces, the stronger surface tension, and capillary action is going to depend on the attraction between the molecules with themselves, or the attraction between the molecules and the container or the glass wall where they are. And then we talk about phase changes, heating or cooling curve. We talk about all the different states, like solid, liquid, gas, and melting, boiling, and all that. We talk about endothermic and exothermic. We were able to draw heating curve. We became aware of enthalpy and how to find it, and how to use it to calculate energy or mass or anything like that. And then we were just introduced to phase diagrams and all the topics that we just mentioned a few seconds ago. And ladies and gentlemen, with that, we have officially finished chapter 12. You start seeing recorded lectures on chapter 13 happening this weekend. So thank you very much. Thank you for listening. Hopefully I didn't bore you on this chapter. I will try to do my best adapting to this new environment for me, the online environment. So talk to you later. Have a great weekend.